So let's take a moment to look at the derivatives of the hyperbolic functions. And here's where we notice another strong similarity with the trig functions. The derivative formulas here are going to resemble them very strongly. So the derivative of hyperbolic sine, for instance, is equal to hyperbolic cosine. The biggest thing that will be different here is that the derivative of hyperbolic cosine is actually equal to hyperbolic sine, so it actually doesn't change to a negative there like it would for, so that's one that's different, right? For we know that the derivative of cosine would be negative sine, but for hyperbolic cosine stays positive. And as a result here we see that that holds true for secant as well, where it's the opposite sign. So hyperbolic secant, the derivative is negative hyperbolic secant h, or sorry, negative hyperbolic secant x, hyperbolic tangent x. Otherwise, the other ones are going to be very similar, like the derivative of hyperbolic tangent is hyperbolic secant squared. And the other ones are the same. So those are the only ones that are a little bit different, but just barely different. So let's practice using these formulas. So the derivative of hyperbolic cosine of the square root of x. Well, we saw the derivative of hyperbolic cosine is hyperbolic sine. And in this case, we got the square root of x in there. So then we'll just multiply by the derivative of the square root of x, which we know is 1 over 2 square root of x. So it'll be hyperbolic sine of x over square root of x over 2 square root of x. Or here we've got ln of hyperbolic sine of t. So the derivative will be 1 over hyperbolic sine of t times the derivative of hyperbolic sine of t, which is hyperbolic cosine of t, which now we've got hyperbolic cosine over hyperbolic sine, which we know that's the way we've defined hyperbolic cotangent. Now let's take a moment to look at the inverse hyperbolic functions. And for hyperbolic sine and hyperbolic tangent, these were both one-to-one functions. So there wasn't any need to restrict the domains, but we did need to restrict the domain for hyperbolic cosine because it was not one-to-one, so we're restricting it so that we're just taking the part of its graph that's to the right, and then making that restriction that x is greater than or equal to 0 so that we can find the inverse. Okay, so here we see the graph of hyperbolic sine here, inverse, hyperbolic sine inverse. Here's the graph of hyperbolic cosine inverse. Right, notice that it's missing the other half there to make it one-to-one. And then here's the graph of hyperbolic tangent inverse. So there's going to be an algebraic formula that we can then develop to find each of these inverse hyperbolic functions. So the inverse hyperbolic function, we have one for sine, cosine, tangent, can be solved out algebraically. This is what they would look like, and we'll go through one of them here. We'll go through hyperbolic sine to show how we can derive that formula. So in this case, hyperbolic sine inverse is ln of x plus the square root of x squared plus 1. So when we want to work this one out, we're really looking for a solution, right? So suppose we want to get an expression for y in terms of x here. Sorry, I need to use hyperbolic sine. So then we know x is going to be hyperbolic sine of y. So our goal really should be to try and solve for y in terms of x using this equation here. So we can define it as e to the y minus e to the negative y. That's using the definition of hyperbolic sine. And our goal would be to try and solve for y in terms of x here, to get an expression for the hyperbolic sine inverse of x. So here I'll multiply the 2 to the opposite side. And actually, one thing I want to keep in mind is that in this case, remember, we had to make a restriction on y. Y had to be greater than or equal to 0. That'll be important here when we're going through it, but I'll just mention it here to remind ourselves later on when we need that. Okay, and the trick here is, well, we've got an e to the y minus e to the negative y. The trick here is to multiply through this equation by e to the y, so that this becomes e to the 2y minus 1. Right, so I just multiply both sides by e to the y there to get there. And now we get something that almost resembles a quadratic equation. So if I bring all the terms here to one side, we actually have a quadratic equation if I substitute e to the y. So here I'm just going to replace e to the y with a different variable, say u. And we can kind of see here, yeah, that this would be e to the y squared, so that would be u squared minus 2x e to the y would be 2xu. Okay, now we just have a quadratic equation in the variable u. So I'm going to use quadratic formula to solve for u. So it would be negative b, which would be negative 2x, so 2x plus or minus the square root of b squared would be 2x squared, so that would be 4x squared. Minus 4ac, so 4 times 1 times negative 1, all over 2. So we got 2x plus or minus the square root of, let's see, so that'll be 4x squared plus 4 inside the square root. Over 2. And then I can also factor out the 2 from inside I can factor out a 4, which becomes 2 outside the square root. So this becomes and now I divide out the 2 and we get x plus or minus the square root of x squared plus 1 over, oh, no, not over 2, so we divided out the 2. So there we have it. And remember, this was actually solving for u, which was e to the y. Now here's where we have to be careful. I left the plus or minus here because maybe it wasn't obvious that we could have both, but here we need to actually pick one, and in this case we would have to pick the positive one because we could never have an e to any power that's going to come out to be negative. So the only way this is going to have a valid solution is if x e to the y is a positive value, right? So x plus the square root of x squared plus 1 is going to give us a positive value, whereas on the other hand, x minus the square root of x squared plus 1 could possibly be a negative value. So we don't want to give ourselves that possibility. But we're basically there. Now we can solve for y to get y equals ln of x plus the square root of x squared plus 1. So we have our formula for secant inverse hyperbolic, sorry, not hyperbolic sine inverse. it was just a bit of an algebraic problem, solving this equation using a little bit of algebraic trickery. So you could do that for hyperbolic cosine and hyperbolic tangent as well. But we'll leave it at that for hyperbolic sine.